So I'd like to present you our work, which was conducted with Gilles, Géry Casiez, Lecolinet, and also Marc Teyssier. So what do we do in this work? We're actually trying to understand if using head motions is an efficient modality for controlling the viewpoint in a 3D scene. So I'd first like to go through motivations. So here is a quick video to show you issues that we encountered when we interact in 3D environments. So we have a 3D scene which is projected on a 2D screen, so we lose the depth perception. So what we actually have here is we can encounter occlusion. For example, behind the green teapot there is a red target, but it's very hard to perceive. And also on the right side of the screen you have two targets, but it's hard to perceive how they are, at which depth they are compared to each other. So it's hard to understand the relation between objects. So we have both occlusion and limited depth perception. So a way to solve this issue is actually to control the viewpoint and to do various movements in the 3D scene. So that's what is usually done. Like, for example, in this Blender modelization, the user will move around the 3D scene to better perceive what is modeling. The thing is, this requires many transitions between camera control and editing. As you can see, it's always switching between the two tasks. So we have many transitions between editing and controlling the viewpoints, and this is because we're using the same modalities to do both. So we're both using the mouse and the keyboard to do this kind of modalities. So the cause of this is that we have sequential operation. We have to go through viewpoint manipulation, and then we can do editing, and then go back to viewpoint control, etc. So the goal of our work is to favor efficient and natural techniques for viewpoint control, which would allow task parallelism by leaving the hands free to actually do some modelization, and this way would also increase interaction bandwidth. So since we're always looking at the screen, because we're always facing it with the head, why not using the head to control the viewpoint, and this way have the hands free for doing some editing task and using the head to control the viewpoint. So there has been some works in this. There's been some work using the head in many different domains, such as in virtual reality, or in video conferencing, video games, or for drone control, or also in mobile interaction. And here is an example of, so this is head-coupled perspective, which actually solves this issue that we had before with the depth perception. Here we have motion parallax, depth Q, which we didn't have before. So this is great because it gives you a better sense of the depth, but at the same time, it's lacking several things. So it's good for immersion because it really feels intuitive, right? But you have low amplitude doing this because usually it works using the translation of the head, and you cannot do a full turn in the 3D scene, so you cannot perceive all the objects from, you cannot turn around the whole scene. So actually, which camera movement is adapted to have a preview of the whole 3D scene, and which head movement should we use to control this camera control? So we conducted interviews and we had a few observations, and there are several existing camera controls. There's like translation, then you have also two types of rotations, such as egocentric rotation, where the camera is rotating on itself, and exocentric rotation, where the camera will be rotating around a certain point in the scene, which is not its own center. And we found out that orbital control is actually enables the user to quickly view a 3D scene from different perspectives, is also frequently used in room planner applications or modeling softwares. And it's actually fairly intuitive to use the head to control this kind of head rotation. So now we know that we want to do orbital control, and now I would like to tell you about the whole approach that we followed in this work. So we want to do orbital control. We have to study we have to know how to map the user's movements to this orbital control. So we have to do a study to evaluate the user abilities. For example, to know which head axis we're going to use for the head rotation, and also what is the widest amplitude that it can perform facing the screen, and also at the same time, what is the smallest control that it can actually produce. Not noise, but something that it can effectively control. And finally, we have to evaluate the system resolution, the sensor resolution that we use to capture the user input, because if the system is not precise enough, is less precise than the user, then we cannot really efficiently use it. So let's start with the system resolution. We first had to, there are many different sensors that we can use to get the head 6 degrees of freedom. You can either use a Kinect, a webcam, just to cite a few. For example, in real applications, we would probably use a Kinect or a webcam. But here, since we wanted to have really precise measurements, we went for infrared tracking system. So we're using, it's not a Vicon, it's a ART system. So we have a special room with the system installed with 8 infrared cameras and a passive to target that we actually screwed on a special helmet for, I don't know what it's called in English. So what we did is that we measured the device resolution, so the tracking system resolution, and we evaluated it to 0.05 degrees. And we also measured the user noise to be 0.2 degrees. So this means that we can perfectly use the system to get the user input because it's precise. It's actually more precise than the user noise. So the next step, now that we know this, was to understand which head axis we would use. So there are 3 different axes that we can use. There's the yaw, the pitch, and the roll. So what we did is that we conducted a study to understand what were the most suited axes for controlling orbital control in the scene. And we want to do, actually, I didn't say it, but that's vertical orbital control. We want to rotate around the vertical axis. So many participants were using the yaw to control this axis. Some of them were proposing the roll, but nobody proposed the pitch because it didn't seem intuitive enough. So actually there was a majority of people proposing the yaw and some of them proposed the roll. So we went for these 2 axes in the following experiments. So the next step was to determine what is the widest amplitude that users can perform. And we call this the maximum comfortable amplitude. This is the amplitude that they have facing the screen. So there are two criteria. There is visual comfort, which is they should always have the screen in sight. And fatigue, they should never, ideally, it shouldn't be tiring for them. So the protocol was the following. We had them move to resting position. Then we gave them a task where they had to rotate the head at the widest amplitude they could perform on a certain axis, and then read a word. They should remember this word, and the next step of the trial was to show them a distractor grid, and they had to find the word into this distractor grid while keeping the head at the same position. So here's a trial example. There is a word Zen here, and the user has to find it into the word grid. And so what we found out is that, so facing the screen, the user had a comfortable amplitude which was wider on the roll than on the yaw, which seemed quite, that was not intuitive, right? We would expect to have the opposite because it's well known that we have more amplitude on the yaw, about 70 degrees amplitude, and roll we would have 40 degrees instead, when not facing a screen. But facing a screen, it's quite different because actually when the users move on the yaw, the screen will shift out of the sight, so we end up having less amplitude on the yaw than on the roll. So 35 degrees on the roll and 26 degrees on the yaw. So now that we have the widest amplitude that the user can perform, we were interested also to know what is the smallest movement that they can effectively control. So in order to do that, we used a protocol which was used successfully by Aceituno et al. This was used to measure the smallest controllable movement which could be done with a mouse. We reuse it for the head. So the protocol was the following. We first asked the user to place themselves at a home position, then to perform a rotational head movement which was inferior to an amplitude that we picked. So we went from a large amplitude and we repeated this step up to the point where we had, so we repeated this step by reducing the amplitude every time, and we stopped when we had a success rate which was below 95%. And we found out that head useful resolution was 1 degree on both axes. So now that we evaluated the user abilities, we needed to do the mapping. So how do we transform the user input into the camera control? So in order to do this, we have to use a factor which is called the control display gain. What does it stand for? So the control here is the user input, so that's the head movements, and the display is the output, the camera control. And the control display gain is the ratio between the display and the control. So what does it mean exactly? It means that if you have a gain which is inferior to 1, then you have lower amplitude, but you have increased precision. Because the movements that you do wider movements with the head, then you get movements, then the camera moves in the 3D scene. So you actually you have increased precision but lower amplitude. The opposite is that when you have a gain which is superior to 1, you would have increased amplitude but lower precision. You actually amplify the movements. So what we did here, our goal was to have to be able to control 180 degrees in each direction with the yaw and the roll. So that's for the yaw here. We divided, to get the CD gain, we divided the amplitude that we wanted to effectively reach by the widest amplitude we could perform on this axis, and we obtained an amplification factor of 6.9 degrees, of 6.9, sorry. And for the roll, we did the same, and we obtained 5.1 as a CD gain value. So here is a mapping summary. So we want to be able to perform 180 degrees. We have an amplitude of 36 on the roll and 35 on the roll and 26 on the yaw. This helps us to get the gain value. And we have a useful resolution, which is 1 degree. So there is no, the smallest target that we can acquire on both of these axes is 1 degree. So as the smallest movement that we can do is 5.1 or 6.9, there is no issue on this part. So what we did next is to compare both of this technique it was kind of docking task. So we had first the user move to resting position, then pick up an object on the ground. Here was a ball. They would pick it up with the mouse. Then they would align with the target in the scene using the technique that we defined, either on the yaw or on the roll. And then they would shoot at the target and return to home position. So here is a sample video showing what we were doing. So first the user picks up the ball and then align with the target. It shows as green when it's aligned, and then he can shoot to the target and return to home position. We found out that roll was actually more accurate than yaw, with 92% success rate on the roll and 88% on the yaw. This was kind of predictable because we have an amplification factor which is less on the roll than on the yaw, so we have logically more precision. But roll was also faster than yaw. We had a completion time of 4 seconds on the roll and 4.6 seconds on the yaw. So the next step was to evaluate our technique against baseline technique. So we had to, we wanted to evaluate external validity of this technique. So here is an example of a task which is often done in 3D. So you have an object and you want to displace it to another position, which requires both to be able to manipulate the object, displace it in the 3D scene, and also control the viewpoint. So in the 3D task that we used for the next experiment was based on this. We had 3 different techniques. We had either, so we had a first block of experiment and then a post-experiment. During the first block, we had the participants were using either the roll technique or the mouse plus keyboard technique. Here we use the same bindings as in the Blender modeling software. So the keyboard would be used, for the mouse keyboard technique would be used to control, so it would have a specific step, not something which I think was about 10 degrees per iteration with the keyboard, and the mouse would allow continuous control. For the roll technique, the viewpoint control would be done with the head, and for all these techniques, the object manipulation would be done by dragging the axis of the object using the mouse. And in the post experiment, we had the user choose between using the head or the mouse and keyboard, so they could pick their preferred technique. So the process of the experiment was the following. First, move to resting position. Then they could control the viewpoint to reach a 3D object. And then they would dock the 3D object into a target and return to home position. So here's a sample video. So the participant move an object into the green sphere so it can actually dock the object into the green sphere to finish the trial and then return to home position. What we found out is that head roll was faster than mouse keyboard. We had a total completion time of 9.8 seconds with the mouse keyboard and 8.3 seconds with the roll. So we had significant results. We had 14.5. We were 14.5 faster using the roll technique than the mouse plus keyboard. Also, the free technique was even faster. We had about 7 seconds average with the free technique. This is interesting because during the free technique, participants all of them were using most of them were using the head roll, and some of them were also using the keyboard with the head roll. So what we did next is to use a webcam and actually implement on an application this technique. So here is an example of a thing which can be done. It's a room planner application, so the participant can either displace objects in the software using his hands and control the viewpoint with its head, or even draw on a piece of paper and control the viewpoint with its head in the software. This can be done using various sensors, but each of them have their pros and cons. For example, the webcam, it's integrated in most computers, in most laptops at least, but it requires often intense processing. It's not so precise and doesn't work in low light. The Kinect is quite cheap. It has good precision, but it also requires quite a lot of processing. It's not so small and it's not really integrated. And our infrared system, it's really precise, but it's very expensive, and you need a full room to operate this thing. So another approach would be to use a gyroscope, IMU. So it's cheap to fabricate. It works in low light and it's very small. However, there is calibration required, but usually it takes like 20 seconds. And it also needs to be worn. So what we did is that we hooked this with Arduino Nano. I think that was about like $30 all in all. We installed this on the headset, and then we hooked this with the Blender application. So now I can control the viewpoints in Blender using this device. So to sum up, we had 4 studies conducted. We first found out that the widest amplitude that user could perform in front of the screen was about 35 degrees on the roll and 26 degrees on the yaw. We found out that the smallest movement they could perform willingly was about 1 degree. We found out that roll was faster and more precise than the yaw. And I guess the baseline roll was also faster than mouse keyboard, and was also preferred in the free condition. So thank you for listening to my talk, and I'm ready to take your questions.
Hey, Yongguang Kim from Casiez. It's an interesting approach. So instead of mapping full ranges of camera motion with head motion, have you considered some clutching techniques or keep moving on the edge conditions, just like conventional mouse navigation controls?
Yeah, so that's a really good question. We thought about it, so not as a replacement, but more as a way to be able to recalibrate. Like, you don't want to have your head stuck at the same point all the time, so you would just press the space bar or any button, and the scene would recalibrate at this point, and then you could move your head back. So a way to kind of clutch, recalibrate the position of the zero position in the scene.
Okay, thanks.
Hello. You mentioned some of your kind of main applications of this were in 3D modeling and moving around 3D environments, something that would require pretty frequent camera motions. And you mentioned that you looked into kind of short-term fatigue and how you would move your head too far. But did you notice any, kind of negative side effects of long-term fatigue, of needing to move your head around for long periods of time?
I think we would need to conduct a full study on this. We didn't run any long studies on the effect of what this could cause on the user fatigue. Yeah, that would be something that we should do probably in future work.
Thank you.
But yeah.
I actually will add another question that's kind of related to the first one. In the video, you seem to inadvertently activate the head rotation by just moving your head. So the idea of clutching is actually a good idea because you kind of want that only when it's intentional, right? Can you elaborate on that?
So you mean activating? Okay. So we also have some leads about activation. For example, we thought about having a zone that we would define in the space around the user, which would in this zone, the user would not activate the technique, but if he crosses this zone, if he goes out of this zone, then it would trigger the technique. So either something which would require clutching some activation by pressing a button, or something which would be just monitoring the head position of the user and activating it at a certain point.
Quick question.
So there are multiple ways to roll your head. Did you notice any users using their bodies instead of actually rolling their necks?
So we actually wanted them to move their neck more because that's what we studied in the pre-study experiments. We really wanted them to only move their head on the sides. We did some studies before with using full body, but I think there's just another approach here. We really wanted to do that. I don't know. I'm sorry. I think it's just a choice, but we could probably go with the other approach and study it as well. I'm not sure if it's easier for the user, if it's less tiring. That should be something that we should study probably.
Okay, let's thank the speaker.